Welcome to Electrical Engineering with Excel. This is a series of videos to help you make Excel workbooks for various electrical engineering problems and circuit calculators. This is an introduction to creating user-defined functions. The first one will be very simple, and in later videos, we will develop more complicated user-defined functions. So what is a user-defined function? They work just like standard Excel functions, except you define how they work. It uses Visual Basic for Applications, or VBA, programming language. It takes in data as arguments, like ordinary Excel functions. It performs some sort of calculation or process on the input arguments, and returns the desired result. As an example, this function calculates the area of a triangle. It takes the base and the height, and calculates the area and returns the result of the triangle area function. It's used in the spreadsheet the same as any other function. We will start with something simple but useful. We will develop a couple functions related to the American wire gauge. Here's a little background. It's also known as the Brown and Sharp wire gauge, as they were the ones that developed it. It's a logarithmically stepped, standardized gauge system. It's been used since 1857. The increasing gauge number corresponds to a decreasing diameter. This gauge system originated in the number of drawing operations used to produce a given wire gauge. Wire is forced through the draw plate. It comes out elongated and thinner. It may be drawn through yet another smaller diameter draw plate. The more drawing operations, the smaller diameter, so the increasing gauge numbers mean smaller diameter. The defining gauge is 36 gauge and is 5/1000ths of an inch diameter. The largest gauge, Alt4, is 92 times larger at 0.46 inches diameter. There are 39 gauge numbers, or steps, between those gauges. Here are the gauge numbers for each step and their associated diameters. The common ratio for the geometric progression will be the 39th root of 92, or 1.229322, with the base gauge being 5/1000ths of an inch for 36 gauge. To get the diameter for 35 gauge, multiply 5/1000ths by the common ratio to get 5.6/1000ths of an inch. Here's a general equation for calculating the diameter of a specific gauge N. You can see if the gauge is 36, the exponent becomes 0, and the result is 5/1000ths of an inch. Using this law of exponents, the equation can be simplified to this. By the way, the American wire gauge was extended to gauge 56 in 1961. You can use negative numbers for N gauges larger than 0. For example, use -3 for 4/0. By default, you will not likely have the Developer tab on your command ribbon. To add it, click the File tab, then Options, then Customize Ribbon. Under Customize Ribbon, click the Developer box and OK. You will now have the Developer tab. Select it and click Visual Basic. This brings up the Visual Basic editor. Select Insert and Module. It by default creates Module 1. This is where you will put in your code. The first function I'm calling AWG DIA will take in a gauge number argument and return the diameter of that gauge in inches. Here's the module window. The user-defined function is simply the word function followed by the function name, AWG DIA, and the arguments in parentheses. In this case, there's only one argument, the gauge number. To return a value, simply set the function name equal to the desired result, then the end function. This is all that's needed to calculate the diameter, but there are a couple more things I'll add. The gauge argument is meant to be an integer. If the user inputs a non-integer, you will get a diameter that is mathematically equal to a non-integer gauge, but it will not be a true wire gauge diameter. I'll set the variable R gauge to equal the gauge input rounded to 0 decimal places, which will be the closest integer to the input. The first argument of the round function is the input value, and the second is the number of digits to be rounded. The single quote character is for comments. Any text past the single quote is displayed in green as a comment. A second feature we will use is raising an error if the input gauge is less than -3 or greater than 56. We will use a simple if statement with a logical OR operator to proceed if the R gauge value is lower than -3 or greater than 56. If true, we will use the error raise method. This method requires a number after it, which is a user-defined error number. The VB object error constant is equal to this big negative number, and from what I can tell, is the recommended starting number for errors. Since we are not tracking any other errors with this code, we don't need to add any number to it. Now I'll go paste in our code for the AWG diameter function. I'll go to the spreadsheet and enter 30 as a wire gauge number, and then use our AWG diameter function and make its argument cell A1. There we have the diameter of 30 gauge wire, which is about 10/1000ths of an inch. Now you may be asking yourself, what is the practical use of an Excel function that returns the diameter of the American wire gauge? If we were designing cables, we would be concerned about the wire resistance. To calculate the wire resistance, we need to know the cross-sectional area of the wire, and therefore we need the diameter of the wire. To calculate the resistance of a wire, we need to know and understand the property of material called resistivity. I'm sure you are familiar with it, but I thought a quick review would be useful. Resistivity is represented by the Greek letter rho. The SI unit of electrical resistivity is the ohm meter. For example, if a 1 cubic meter material has sheet contacts on opposite faces, and the resistance between those contacts is 1 ohm, then the resistivity of the material is 1 ohm meter. The resistivity of copper is 17.24 nano-ohm meters. Rho is equal to R times L over A, where R is the electrical resistance in ohms, L is the length in meters, and A is the cross-sectional area in square meters. Now putting the units in the equation makes it clear why the unit of rho is the ohm meter. Here it's arranged to solve for resistance. What we will see is that it's cumbersome to calculate the resistance of a wire when the units are in meters. As an example, let's take 30 gauge wire. The diameter is 10/1000ths of an inch, and the length in this case is 1 foot or 12 inches. We must convert the diameter to meters and the length to meters. Then we need to calculate the area, halving the diameter to get the radius, and involve pi. We get 0.1038 ohms resistance. This took a lot of unnecessary work. Next, we will demonstrate a more convenient system for units of resistivity. One of the extra steps with calculating the area of the wire using a radius squared was involving pi. Back in the days before calculators, some genius came up with an idea of the diameter being in the units of circular mils. Of course, a mil is 1/1000th of an inch. The area in circular mils is the diameter of the wire in mils squared. That's greater than the actual area, but that can easily be accounted for. What's fundamentally relevant about circular mils is that it's a diameter that is squared, so it's still proportional to area. We just need to account for the difference in the true area versus the area in circular mils. Consider a unit circle with its radius being 1. The area of the unit circle with the radius being 1 is simply pi. Now consider a square outside the unit circle. One side is 2 times the radius of 1, which is 2. The area of the square is one side squared, so this outside square area is 4. The true area is equal to the diameter squared, or circular mils. The ratio of the outside square to the unit circle is 4 over pi. Now that we've got that out of the way, we can scale our resistivity units to not only use circular mils for area, but use length in the unit of feet. Of course, 1 meter is very close to 39.37 inches. There is 39.37 squared inches per square meter. There is 1,000 squared square mils per square inch. We just showed there are 4 circular mils per pi square mils. And finally, there's 39.37 divided by 12 feet per meter. Going through the math, 1 ohm meter is equal to 6.015 e to the 9th ohm circular mil per foot resistivity. If you try this on your calculator, you won't get this number exactly. This big number was calculated with the full precision of inches per meter and pi. The resistivity for copper we cited earlier was 17.24 nano-ohm meters. Scaling that equals 10.37 ohm circular mil per foot. This makes calculating the resistance of wire very simple. Let's do 36 gauge, which is 5 mils diameter and a length of 1 foot. Recall the equation for resistance, we use the rho for copper we just got. Recall the equation for resistance, we are using the rho for copper we just scaled at 10.37. The area of the wire is 5 squared, or 25 circular mils. The resistance comes out to 0.4148 ohms. We will now put this to work in Visual Basic to calculate wire resistance per foot of a given American wire gauge number. I copied the code from the diameter function since we will need to calculate the diameter of the wire before we can calculate the resistance. I renamed the function to AWG Res and set the diameter calculation to the variable DIA. I then set the function name to AWG Res to 10.37 divided by the diameter times 1,000 squared. Now I'll go to the Visual Basic editor and paste the AWG resistance code. Going back to the worksheet to enter the function using the same gauge argument of A1 as before. And there we have it, 0.10318 ohms per foot. It's worth mentioning stranded wire. There are many variations, but stranded wire often uses 7 or 19 strands, since that makes a nice circular bunch. The overall physical diameter of the strands is, of course, larger than the solid equivalent. Here's an example of a 20 gauge wire made up of 7 strands of 28 gauge. The gauge of the individual strand is typically rounded up to make the total cross-sectional area be slightly more than the solid equivalent. In this case, the total cross-section of 7 strands of 28 gauge is 109.5% of the solid equivalent. Here's a 20 gauge stranded set with 19 strands of 32 gauge. The total cross-section of the 19 strands of 32 gauge is 117.6% of the solid equivalent. In these cases, the resistance of your wire will be slightly less than that of what we calculate here. That's hardly ever a bad thing. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.